Hello friends, I welcome you in lecture number 5 on elementary analytic functions. In this lecture we are going to talk about complex exponents. We will define complex exponents and then we will do some problems on how to find out power of complex numbers. So let us start with the definition. Suppose z is any non-zero complex number and c is any complex number. Then the function z raised to c is defined as z raised to c equals e raised to c into log z. So here we are using the complex logarithmic function which we have discussed in previous two lectures. You can watch those two lectures if you have not watched them to understand this lecture. But we can recall the definition of log z is ln mod z plus I times argument of z. So because we have logarithm of z, we have started with non-zero complex number z. So z raised to c is defined as e to the power c log z, where log z denotes the multiple valued logarithmic function. Now in log z, if we take instead of general argument, if we use principal argument, then the value of log z is denoted by capital log z and is known as principal logarithm. So if we use principal logarithm in this definition, then the value of z raised to c will be unique. So that particular value z raised to c equal to e raised to c log z is called the principal value of z raised to c. So if you are asked to find out principal value of z raised to c, you have to use principal logarithm in this definition. So we consider some examples on this definition. First example is we have to prove that I to the power minus 2i is e to the power 4n plus 1 pi n belongs to z. So we start proving this. So if we compare this with z raised to c, we can start with z equal to I and c equal to minus 2i. So first we find out log z. Log z is log I, and by definition of logarithm we have log I equal to log mod I plus I times argument of I. Now modulus of I is 1, and as we know I is on y-axis, so argument of I is pi by 2 plus 2n pi. Okay, just for understanding, I is somewhere here on y-axis, so argument is nothing but angle made by this vector with positive x-axis, which is pi by 2 here. Now this log 1 is a real logarithmic function, so it is 0, and this we can rewrite by taking pi common, and also we can take LCM, so it is going to be 4n plus 1 pi I by 2. So therefore log z is 4n plus 1 pi I divided by 2. So now we find out principal value. By definition, z raised to c is e raised to c log z. So here z is I, c is minus 2i. Let me check again. Okay, z is I, c is minus 2i. So this is by definition e raised to minus 2i log I. And log I is nothing but 4n plus 1 pi I by 2. So we substitute that value here, e raised to minus 2i 4n plus 1 into pi I by 2. So you can see here 2 will cancel out, and I into I is going to be I square, that is minus 1. And we are left with 4n plus 1 times pi. because I into I is I square, that is minus 1, and minus 1 into minus 1 will be positive. So this is nothing but this we can rewrite as exponential of 4n plus 1 times pi, and this left hand side is nothing but I to the power minus 2i. So in this way it is easy to find out complex exponents if you have knowledge of complex logarithmic function. So we can do some more problems. Here we are asked to find out principal value of minus I to the power I. So as we have discussed, principal value of complex exponent is given by e to the power c, principal logarithm of z. So if we compare with z raised to c, here z is minus I and c is I. So first we find out principal logarithm of z. So by definition ln z is ln mod z plus I times principal argument of z. Z is minus I, so ln minus I is ln absolute value of minus I plus I times argument of principal argument of minus I. Absolute value of minus I is 1, so here I have to write ln 1 plus I times minus I is on negative y-axis, and here we require principal argument. So either we can measure in this counterclockwise or clockwise, but if we measure counterclockwise, angle will be greater than pi, but our angle must be in between minus pi and pi. So if we measure clockwise, angle is minus pi by 2. So we consider minus pi by 2 because it is in between minus pi and pi. And this log 1, left hand side is log minus I. Now this is real logarithmic function, so its value is 0, log 1 is 0, and this we can write as minus pi I by 2. Now once we obtain this logarithmic function of minus I, we can find out minus I to the power I using this definition. So now principal value of z raised to c is e to the power c capital log z. So therefore here z is minus I, c is I. Z is minus I, c is I. So here we put c equal to I, c is I, and log of minus I, and log of minus I is minus pi I by 2. So this is e to the power I minus pi I by 2. So and this we can simplify as e to the power minus pi I square by 2, and because I square is minus 1, we obtain e to the power pi by 2. I square is minus 1, minus 1 minus 1 will be positive. So principal value of, I shortly write principal value of minus I raised to I is e to the power pi by 2. So it is easy to find out complex exponents. You must have knowledge about argument and logarithmic functions. We can have one more problem. Find principal value of e by 2 minus 1 minus root 3i to the power 3 pi I. So if we compare with z raised to c, here z is e by 2 times minus 1 minus root 3i, and c is 3 pi I. So I have to first find out log of z. Before that we find out absolute value of z, which is nothing but absolute value of e by 2 times minus 1 minus root 3i. This is absolute value of e by 2 is e by 2. It is real number. And absolute value of minus 1 minus root 3i. So this is by definition square of minus 1 plus square of minus root 3, which is 3. So this is going to be under root 4, and under root 4 is 2. So absolute value is e. So therefore absolute value of z is e. Now we find out argument of z. So we can see this complex number is in third quadrant. So for argument we must have the location of our complex number in the xy plane. So suppose this is e by 2 or minus e by 2, and suppose this is minus e by 2 root 3i. A real part of this complex number is minus e by 2, and imaginary part is minus root 3 e by 2. Okay, so x, if we compare with x plus iy, x is minus e by 2 and y is minus root 3 times e by 2. So if we consider this vector representing this complex number is minus e by 2 or e by 2 times minus 1 minus root 3i. This is the vector represented by this given complex number is represented by this vector, and this is the location of this complex number e by 2 minus 1 minus root 3i. Now if we extend this in first quadrant, then suppose this is extension in first quadrant, so it is going to be 1 plus root 3i. So first we find out this angle using the formula that tan theta is imaginary part divided by real part. Here imaginary part is root 3 times e by 2, real part is 1. So if we consider division of imaginary part with real part, we will obtain tan theta equal to root 3. So this gives theta is pi by 3. So this angle is pi by 3. Now because this angle is pi by 3, this is also pi by 3. And this angle is going to be pi by 6. Now we are interested in the principal argument. So if we measure angle made by this vector with positive x-axis in counterclockwise, then you can see this angle is going to be, this angle is pi by 3 and up to this it is pi. So it is going to be pi plus pi by 3. So it will be bigger than pi, and here we require principal argument of the complex number. So we have to measure in clockwise direction, that is in this direction we have to measure. So if we measure in this direction, then we can see this angle is pi by 6 and this one is 90 degree, that is pi by 2. So this total angle made by this vector with positive x-axis is nothing but pi by 2 plus pi by 6, and this we can rewrite as minus 3 pi by 6 plus pi by 6, which is minus 4 pi by 6, and cancelling 2 we have minus 2 pi by 3. So this shows that argument of z, principal argument of z is minus 2 pi by 3. So now once we have argument and modulus, we can find out the logarithm of this complex number. So now log z is ln mod z plus I times principal argument of z. Here I have to find out principal logarithm because I am asked to find out principal value of given complex exponent. So therefore ln z is absolute value of z is e, we have find out. So we put absolute value of z equal to e, and principal argument of z is minus 2 pi by 3. So here we put minus 2 pi by 3. Now because this logarithm is real logarithm, log z is nothing but 1, and this is minus 2 pi I by 3. Now once we have principal logarithm, we can find out z to the power c, principal value of z to the power c. So now principal value of z raised to c is, by definition, z raised to c is e raised to c, principal value of z. Now here c is 3 pi I, so we put c equal to 3 pi I, and log z we have obtained as 1 minus 2 pi I by 3. So 1 minus 2 pi I divided by 3. So this is now this we can simplify. E to the power 3 pi I minus 3 will cancel out, and we have 2 times pi square into I square. Pi I into pi I is pi square I square, 3 will cancel out, and we have minus 2. This we can rewrite by using the property of exponential function, e raised to minus e raised to 3 pi I, and this is e raised to minus 2 pi square, and I square is minus 1. So now again using Euler's formula, e raised to 3 pi I is nothing but cos 3 pi plus I sin 3 pi, and this is nothing but e to the power 2 pi square. Cos 3 pi is minus 1 and sin 3 pi is 0. This is e to the power 2 pi square. So this is nothing but minus 1. So finally we have minus e to the power 2 pi square, which is nothing but principal value of minus e by 2, or e by 2 minus 1 minus root 3 I, principal value of this z raised to 3 pi I is nothing but e raised to minus 2 pi square. So you can see here we must have knowledge of argument and logarithm of a complex number if we want to decide complex exponents. So this is for today's session. I hope you like this lecture. Thank you very much.